Okay, so we were talking about this the other day, okay, and how there's this idea that if you can get everybody to jump at the same time, according to Newton's third law, if you got everyone to jump at the same time in the same place, you could knock the Earth out of its orbit. Yeah, well, there's this idea. I didn't say it was a good one. Okay? There's this idea out there. And Nike literally ran with this. Okay? During the Super Bowl a few years ago, they had this ad called Let's Go. And it was about how the Earth had stopped rotating. It's called the Stopocalypse. Anyway, they were going to get the Earth rotating again by getting everybody to run, of course, in their shoes, okay, in the same direction. And then that would get the Earth rotating again, according to Newton's third law, right? Because if I push on the Earth has to push back, and my force exerting on the Earth, combined with 7 billion other people, should be able to get the Earth rotating rotating again. Stupid. But that's what they did. People thought this was like a real thing that they, because people are stupid. But people thought, yeah, this could work. Okay? So we're going to look at kind of the mechanics of that in terms of not only energy, but also Newton's third law, because it's a way to kind of review those two concepts on our review day here. Okay? And it's also a bit tongue-in-cheek, kind of like the Yoda one we did yesterday, okay, where it's, it's so farcical that it could never happen that it's also kind of, well, silly. All right? So first I'm going to show you Nike's ad that they ran during the Super Bowl, okay, to kind of show you, or give you an idea what people think. So, start of the scenario is the entire Earth's population has been magically transported to one place. Because, well, how would you get everybody to one place other than magic? This will be a problem when we're trying to get everybody home at the end, because apparently there's no magic to do it the other way. Anyway, okay, so the crowd takes up an area the size of Rhode Island, okay? So Rhode Island is the smallest state in the United States, okay? So this is the size of the crowd here, okay? So you packed everybody in like sheep, shoulder to shoulder, okay? It would take up an area the size of the state of Rhode Island. Now, I don't know how everybody jumps when they're shoulder to shoulder like this, but whatever, they're all packed in there, okay? Now, this is our scenario, okay? We're gonna say everybody goes to Rhode Island. Now, are there some logistical problems with having between 6 and 7 billion people all in one place? I can think of one really big, smelly problem. People are going to have to go to the bathroom. And I don't think you can pack in enough porta potties for 7 million people. That's going to get pretty messy, pretty smelly, pretty fast. And then it'll become a toxic biological nightmare. And of course now with COVID, you couldn't possibly social distance 7 billion people all in the state of Rhode Island. So, okay, we'd have all that additional problem. Okay, so the other problem, how do you time this? Okay, how do you make sure everybody jumps at exactly the same moment? I don't know either. Okay, they're saying at the stroke of noon, everyone jumps. Everybody's watch is perfectly synchronized.
Well, like a big billboard. Like a countdown.
Okay, big billboard. Okay, it's not a bad idea. Remember, can I see that from any place in the state?
Have like 1,000 of them.
1,000 of them?
Everybody screams the countdown.
Just have Big Ben.
Okay, Big Ben. Yeah, but here's the problem. That depends on sound. How fast does sound travel? Right? I mean, if there's a track meet going on here, okay, and they're on the far side of the track, they pull the trigger, you see the smoke, and it's like a second later before you hear the sound of the gunshot. Okay? Now you imagine that takes place over the area of an entire state, the sound won't even travel that far. Okay? People don't hear the sound of the starter's pistol here in Mountain View. Okay? The sound doesn't travel that far, and that's not nearly the size of the state of Rhode Island. Okay, we're talking about these massive distances. Okay, and people are like, well, you could just have everybody get a text message on their phone. Well, you know what? When they do that emergency test thing, do we all get that at exactly the same instant? No, it depends on your carrier and the load on the cell towers and all of that kind of stuff. So that's not going to work. Okay, the best idea anyone's ever come up with when I present this problem is they were going to time it so that there were multiple like fireworks. They would do it at night, and the fireworks would be launched from several different places so they could all be seen at the same time. Okay? And then when the fireworks went off, everybody would jump. It's like, that's not a bad idea. It's probably the best one I'd heard for getting everybody to jump at the same time. The problem is everybody's got to be paying attention. I mean, that'd be the problem no matter what. Okay? But you got 7 billion people, and chances are 1 in 7 aren't paying attention at the proper time, and you're only going to get not everybody jumping at the same time because they're not all paying attention. Anyway, okay, so everybody jumps. Okay, so like we were saying, it doesn't really affect the planet very much. Even if we all jump, how hard do we push? Not very hard. Okay. Now here's the other problem. Everybody jumps differently. Okay. How do we make sure that everybody jumps exactly the same? You can't. I mean, what if you have people who can't jump? Okay. Maybe if you got somebody who's in a wheelchair, they can't jump. Okay. They're not part of this. Okay. Somebody with a broken leg, they're not part of this. Okay. Somebody who's, maybe hard of hearing or blind or, they don't, whatever. You got lots of people who aren't going to be able to do the jump. And then you've got the difference in jumps. You got some high-level athlete who can jump straight up in the air, over a meter. And then you got somebody else with the credit card vertical, right? Where if you laid a credit card on the ground, they wouldn't be able to jump over it. Okay? Yeah, that's pretty sad. But you have different levels of athletic ability. You could have a really elderly person who just got a new hip and they can't jump yet. Okay? There's all of these things, that could make this really, really problematic. All right. So on average, we're going to say on average, humans can jump about 0.5 meter on a good day. For a lot of us, that would be a pretty good day. Okay? Back when I was young, that would have been easy, but now that I'm old, it's more like this. Okay? So, yeah, that'd be we'll say 0.5 meter. Even if the Earth were rigid, and that's the other problem, the Earth's not rigid. Okay? Even when I press down, if I'm on the dirt, okay, the dirt kind of deforms a little bit. It's not a rigid surface. Okay? And everyone responded instantly. The Earth would be pushed down by less than an atom's width. Are atoms pretty small? Pretty small. Okay, next, everyone falls back to the ground. Now, technically, the crowd coming back to Earth delivers a lot of energy because they had potential energy and they come back down. Okay, but it's spread out over a large enough area that it doesn't do much more than leave footprints in a lot of people's flower beds. Okay, a slight pulse of pressure spreads north through the North American continental crust and dissipates with little effect. It would probably sound like rolling thunder. To everybody. Okay. The sound of all those feet hitting the ground creates a long, drawn-out roar which lasts many seconds. Eventually, the air grows quiet. Seconds pass. Everyone looks around and starts going, "What is going on? Why did we do this?" Okay. There are a lot of uncomfortable glances. Someone coughs. Everyone freaks out because they think they have COVID. Okay. And then they figure they should start going home. Okay. A cell phone comes out of a pocket. Within seconds, the rest of the world's 5 billion phones follow. All of them. Even those compatible with the region's towers are displaying some version of no signal because the cell networks have collapsed under the load of 7 billion or 5 billion phones. Okay? All right. Outside of Rhode Island, abandoned machinery begins grinding to a halt. There's nobody anywhere but Rhode Island right now. Who's taking care of the nuclear power plant? Or the hydroelectric dam? Or some other thing that needs to be babysat so it doesn't blow up and cause some kind of environmental disaster. Okay? All right. So, the T.F. Green Airport in Warwick, Rhode Island handles a few thousand passengers a day. Assuming they got things organized, okay, including sending out scouting missions to retrieve fuel, they could run at 500% capacity for years and make no dent in the crowd. How do you evacuate all of these people? Okay, this becomes kind of a problem. Okay, so the addition of all the nearby airports doesn't change the equation much, nor does the region's light rail system. Okay, crowds climb on board container ships in the deep water port of Providence, but stocking sufficient food and water for a long sea voyage proves challenging. Okay, Rhode Island's 500,000 cars are commandeered. Moments later, I-95, I-195, I-295 become the sites of the largest traffic jam in the history of the planet. Most of the cars are engulfed by the crowds, but a lucky few get out and begin wandering the abandoned road network. This is something like out of The Walking Dead. Okay? everybody is in one place. All right, some make it past New York or Boston before running out of fuel. Since the electricity is probably not on at this point, rather than find a working gas pump, it's easier to just abandon the car and steal a new one. Who's going to stop you? All the cops are in Rhode Island. Okay? All right. The edge of the crowd spreads outward into southern Massachusetts and Connecticut. Any two people who meet are unlikely to have a language in common, and almost nobody knows the area. The state becomes a patchwork chaos of coalescing and collapsing social hierarchies. This is the Walking Dead part. Okay? Like you've got, the people out behind Negan and the people over here and the Whisperers and all. You've got all these different groups that would eventually become enemies. It would be terrible. Okay? Violence is common. Everyone is hungry and thirsty. Grocery stores are emptied. Fresh water is hard to come by, and there's no efficient system for distributing it. Nobody's mentioned the sewage problem. That would be also a concern. Okay? Within weeks, Rhode Island is a graveyard of billions. So basically, doing this experiment to see if everybody jumps doesn't kill everyone on planet Earth because it knocks planet Earth out of orbit. It's because of a terrible social experiment where, bad things happen. All right, so the survivors spread out across the face of the world and struggle to build a new civilization atop the pristine ruins of the old. Okay, species staggers on, population is greatly reduced. Earth's orbit is completely unaffected, and it spins along exactly as it did before our species-wide jump. All right, so let's have a look at some of these questions here. All right, we talked about what the problems were with the synchronization of everyone's jump. It's a massive area. Sound travels really slowly. You couldn't have a siren or something like that. Using a cell phone signal, the cell phone network would collapse, all of that kind of stuff. Okay, calculate the total mass of the Earth's population, assuming the average mass of a person is 65 kilograms. Okay, so we got 65 times, we're going to say 7 billion people, okay, because that's about what we're at here. Okay, so that's 7 billion times 65. All right, so there's the mass of the entire population of the Earth. Okay, 4.55 times 10 to the 11 kilograms. Now, to give you an idea, comparatively, the mass of the Earth is 5.98 times 10 to the 24 kilograms. Much, much bigger. Okay, that's 14 more zeros, okay, than the other number would have. All right. Calculate the total gravitational potential energy of the crowd when they are at the maximum height of their jump. How high did we say everyone could jump? About a half a meter. Okay, so that's going to mean m times g times h. All right, so we'll take that mass, multiply by 9.81, and multiply by half a meter. Okay, so we got 2.23 times 10 to the 12 joules. All right, that's the potential energy of the crowd. All right, determine the kinetic energy of the crowd as they strike the Earth after their fall. How much? That number, law of conservation of mechanical energy, right? If I jump up, I come back down, and the same amount of energy when I left. Okay, so 2.23 times 10 to the 12 joules worth of mechanical energy, all of it kinetic, when they come back down. All right, law of conservation of energy says energy can't be created or destroyed, but the maximum kinetic energy of the Earth will be less than that of the crowd. Why? Sound, yeah. A bunch of that kinetic energy is turned into other forms of energy, not necessarily all of it doing work on the Earth. So you got some sound, you got some heat, you got the deformation of the Earth's crust, like footprints, okay, things like that, because the Earth is not a rigid surface. All right, so not all of that energy actually does work on the Earth anyway. Okay, all right. So even if it was perfect, the maximum kinetic energy of the Earth would be what number? If all the energy of the crowd got transferred to the Earth, the kinetic energy gained by the Earth would be that number, 2.23 times 10 to the 12 joules. All right, so we want to calculate what the change in speed of the Earth will be as a result of that. So that'll be the kinetic energy the Earth receives equals 1/2 mv squared, where this m is now going to be the mass of Earth. Okay, I want to find out how much the speed of the Earth changes by, assuming it starts at rest and then the crowd hits it, it's going to accelerate to some new speed after that. Is everybody okay with that idea? All right, so I'm going to divide both sides by half of the Earth's mass and then square root, and that will give me the new speed of the Earth. All right, so I've got this number, okay, divided by 0.5 times 5.98 to the 24. Whoop, not to the 2, to the 24. Otherwise, it's going to seem like the Earth would fly out of orbit. All right, and then I got to square root that. Okay, so the Earth's speed is going to change by 1, 2, 3, 4, 5, 6. By that much. Are we knocking the Earth out of orbit? No chance. And the same is true for everybody running in the same direction. Okay? That would have that much effect on the Earth, no matter whether they continue to do it or not. Okay? It's simply not going to make any difference at all. Thankfully. Now, what if Earth gets hit by a really big meteor? Could that do something to our orbit? It would have to be really big. And it would have to hit like straight on, right? Earth has been hit by big objects in the past, okay? The creation of the moon was actually the result of an impact with a Mars-sized object, okay? But it wasn't a head-on crash, it was a glancing crash, okay? That actually re-liquefied the Earth, and the debris was thrown into orbit and coalesced to form the moon. Okay? We know this because the moon is made of exactly the same material as the surface of the Earth. Okay? It doesn't have a solid, like, dense iron core like the Earth. It's made of mostly Earth's surface materials. Okay? Carbon dating and stuff like that from material brought back from the moon landings has confirmed that they basically have the same origin. Okay? Yeah, everybody with me on that? Okay, so kind of a weird one, but yeah, it wouldn't make any difference. Don't worry if you get everybody to jump at the same time. Everyone will die, but not because the Earth goes out of orbit. Okay. Okay, probably want to take out a sheet of paper here. Let's do our exam review stuff here. Okay, give you a minute to get that ready. Okay, first thing we went over in this unit, Newton's first law. Okay, what does Newton's first law say?
When an object is moving at a constant velocity and falls off in the other thing, it will continue moving at that constant velocity horizontally and accelerates downward. Was that second law?
The accelerate part is second law. The first thing he said was right. Okay, an object traveling at a constant velocity will continue to travel at a constant velocity, and an object at rest will stay at rest unless they're acted upon by a net force or an unbalanced force. Okay, that's inertia. Okay, so that's Newton's first law. There's no math, there's no formulas, there's no problem solving to do with Newton's first law. Okay, but we do need to understand its applications. If there's no net force, there's no acceleration. An object will remain at rest or remain traveling at a constant velocity unless there is an unbalanced or net force. That's what Newton's first law says. Okay, that's all there is to Newton's first law. There's really nothing else to do with it. Then there's Newton's second law. This was half the unit. Newton's second law applies to all situations where there is an unbalanced or net force. Okay? There's an unbalanced or net force because the vector sum of all forces law is not zero, like it is in Newton's first law. Okay, so the net force is whatever is left after all the forces have been added together. Okay? What's the other way to calculate net force? Mass times acceleration. Okay, how many different applications of that did we look at? So many, yeah, okay? There's so many applications of it. Okay? Expected on your unit exam, there's gonna be probably 3 problems to do with Newton's second law. What's my favorite? I'm a little hurt. I just don't know what my favorite Newton's second law problem is. It's inclined planes. You're going to have an inclined plane question on the test because that's my favorite kind. Okay, so expect that you'll see one of those. Okay, as well as maybe one that's a bit simpler than that. And Newton's second law getting worked into a few other problems. It's not really the primary thing, but it gets worked into a few other problems in the written response section. Okay, but definitely go over as many different types of Newton's second law problems. Focus on inclined planes because I'm telling you for sure there's one of those. Okay, that are in your worksheet package. One of them, okay, is going to involve vectors. Okay, so looking at your forces of vector quantity worksheet, okay, maybe doing a couple of ones from there. It's probably not a bad idea either, because we did a number of questions where we had like angled forces. Okay, like you had a box, okay, and it was being pulled at an angle, but it was actually moving horizontally, and you had to figure out you had to find one of the forces involved, like what was the force of friction, if it was accelerating at this rate, or I gave you the force of friction and wanted you to find the acceleration. Those are forces of vector quantity type problems. Okay, so expect you're probably going to have something like that, okay, and it will be very similar to one of the examples that we did in class. And then there's some simpler ones, okay, where the only tricky part is actually identifying the forces. Once you have the forces, then everything else is pretty easy. Okay, so big thing would be read the question carefully and draw your diagram. Okay. All right. As part of Newton's second law, okay, we also talked about static situations. Okay. In a static situation, what's the net force? 0. Okay, so static problems, keep that in mind. If it's static, then the net force is 0. Okay, and all the forces add up to 0. The ones we looked at were like elevators traveling at a constant velocity, or signs that were hanging from cables, okay, and weren't moving. Those were static kind of questions. And then we also looked at friction. And one of the questions in the analysis of your energy lab had to do with solving a friction problem, solving for coefficient of friction. Okay? I would expect you'll probably have a Newton's second law question that would involve coefficient of friction, okay, as one of your exam questions. All right, and then we talked about Newton's third law. What do we need to remember about Newton's third law?
Reaction has its equal opposite reaction.
Right. Every action is an equal and opposite reaction, which means forces act in pairs. Okay? Action, reaction, pairs. So if I put 2 boxes together and I push on the first box pushes on the second box, and the second box pushes back on the first box. Okay? Did we do a bunch of 2-box system type questions? We did. Expect to see one. Now, in the end, they were convoluted reasoning, but was there ever any really hard math? Never. Okay? We would have to do sum of all forces and m times a, and that's what we, essentially all Newton's second law problems break down to that. And remember, Newton's third law problems are really just Newton's second law problems. All you have to remember is that even if you're looking for one force, there's a force that's equal to it but opposite. Maybe you find that force instead because it's easier to find that. Okay, that's what all those box problems, okay, are about. And there's a bunch of examples, okay, of those. If you go back in the podcast, we did a whole bunch of those. Might not be a bad idea to watch one or two of them, okay, in preparation for your unit exam on Monday. Okay, after Newton's third law, we talked about work energy theorem. Okay, when is work being done? Okay, when not just kinetic, but potential, or what they add up to, mechanical. Anytime mechanical energy is changing, that could be kinetic or potential, okay, work is being done. In order for work to be done, a force must act over a distance. Force times distance equals the change in mechanical energy. Expect that you will likely have one question that primarily tests that, and one where it's a secondary concept. Okay. But expect it to show up. Okay. Not as difficult as some of the ones we've done. Okay. I did not make it an inclined plane with change in energy on it. Okay. So the inclined plane problem is just Newton's second law. It doesn't have to do with work energy theorem. So the work energy theorem questions I did on this exam are more like the ones you did in your quizzes, where only one type of energy was changing. Okay, so they're actually a bit similar. All right, so here's the big thing. How do I tell the difference between a law of conservation of energy problem and a work energy theorem problem? Because they're going to give me similar data and involve similar situations. They're going to talk about an initial and a final state, both of them. How can I tell the difference?
Conservation of energy is not going to be like talking about forces of friction or something.
Right, okay. In a conservation of energy problem, if they mention friction at all, it would be to tell you to ignore it, or that it doesn't apply, or it's frictionless. Okay? Whereas in a work energy problem, they might tell you what it is. It's this many newtons, and it acts over this distance. Okay? So what you have to do is you have to look at what you're given. Well, they're going to give you similar data and similar situations. A work energy theorem problem is either going to give you a force or ask for it, or ask you to calculate it, and they're going to give you a distance or ask you for it. A law of conservation of energy problem is not going to give you those two things. A law of conservation of energy problem is simply going to say compare points A and B. And it will not mention force, okay? It will not talk about distance unless it's a height, okay? But it's certainly not going to mention force. A work energy theorem problem is always going to involve force, and a work energy theorem problem is going to have an obvious change in mechanical energy. So if you're reading the situation, okay, a law of conservation of energy problem is going to be talking about a situation where the energy does not change. Whereas a work energy theorem problem is going to say, you know, it might even say work is done, or how much work is done, or this much work is done, okay? Or the energy changes by this much, or it's something that's very obviously changing its energy, like it's being lifted, or it's slowing down, okay? All of those situations involve changes in mechanical energy, okay? Everybody kind of follow me there? So you have to read the questions carefully to be able to tell the difference. Okay. Then we talked about conservation of energy, okay, which we've kind of alluded to here. Okay, those would be, you know, like roller coasters, or kids going down hills on sleds, or stuff being dropped off buildings, or anything where gravity is the only force that's acting. Okay, and in that case, energy is going to be conserved because no energy is going to change. Okay, and then yesterday we talked about power, but that's very minor. Okay, all you need to remember about power is that it's how quickly work gets done, not how much. Okay, so there's only 5 concepts in this unit. Okay, only 5. Newton's first law, Newton's second law, Newton's third law, work energy theorem, and conservation of energy. Okay, are there lots of different applications for all of those? Yes. Okay, but in the end, you're only going to be tested on 5 things. All right, your test has. Sorry, I've got to open it up here. I wrote it a long time ago and now I forget. Okay, you have 15 multiple choice. Actually, I think I told you guys this yesterday. 15 multiple choice and 6 written. Okay, so 6 problems, okay, and only 2 of those problems have a A and a B. So there's 6 problems, only 2 of which have an A and a B. Okay, so this will probably feel shorter than the last unit exam, which I know some of you felt was kind of long. Right? So 6 written, 15 multiple choice. Okay, the multiple choice, there's, sorry, Julie, a question?
How many points?
59.
Okay,
I think your kinematics was 63, so they're pretty close. Okay. So in the multiple choice, there's, if there's any calculating, it's really simple calculating. Okay, it would just be like punching something in, basically no manipulation or anything like that. Or if it is a manipulation, it's of like F equals M times A, so it's something really simple. Okay, so it's testing your understanding and some recall. Okay, so what's Newton's first law and Newton's second law? Here's a situation that involves Newton's second law. What would happen? Not necessarily asking you to calculate anything, but what would happen if this was changed according to Newton's second law? So some understanding and application kind of questions, okay, in there. Very little calculating, and what calculating there is, there's one question where you got to subtract, and one where you got to divide. That's it. There's basically no calculating. And then in the written response, okay, you got a fairly simple Newton's second law problem to start it off. Okay, you got the box problem, the 2-box problem. You got the Newton's second law vector problem. You got your inclined plane. You got your work energy theorem problem. And then you got your conservation of energy problem. And it has a part B where I work in work energy theorem. Okay, that's it. That's what's on there. Okay. It felt a little short when I wrote it. But I'm not going to add a question. I'm going to leave it. Okay. On Monday, when you write this test, I will let you write into lunch for 15 minutes. Okay, so class normally ends at 11:36. I'll let you write till 11:51. Okay, is that right? Yeah. So let's write till 11:51. So you get 15 extra minutes, okay, to write if you need it. I don't think you will, but if you do, you have it. Okay. All right, questions from you guys? What kind of things do you want to ask or go over? Or
One where you have the equal and opposite forces on the box.
equal and opposite forces on the box. Okay. So a 2-box problem? Okay. Okay. Okay, I pulled these numbers out of my head, so I hope they work. All right, so here's the situation we have. We have a 20 kilogram box and 15 kilogram box in contact with each other, okay? There's a force being applied to the first box of 80 newtons. The boxes are accelerating at 1.2 meters per second squared to the right. The force of friction on box B is 22 newtons. I don't know what the force of friction on box A is, but I want to calculate the force that A exerts, on B. No, sorry, I had that right the first time. Force B exerts on A, sorry. Give you a couple minutes to try that one before I do. So the force that they're asking me to find is a force that's acting on box A. Agreed? Okay. How much information do I have about box A? I have the force applied, and that's it. How many forces are acting on box A? 3. The applied force that I was told, the 80 newtons, okay, the force of friction, and the force of B acting back on A, which is the force they want me to find. Okay, how many forces are acting on box B? 2. The force of box A and friction. Okay? Those are the only 2 forces acting on box B. And I know one of them. What's the other thing I know? I can calculate F net, because I know the mass of box B and I know its acceleration. Since there's only 2 forces and I know one of them and what they add up to, I should be able to calculate the one I'm missing. Now, the one I'm missing is the force of A on B. They want the force of B on A. Is that okay? Because those 2 forces they're the same but opposite in direction. So that's the convoluted reasoning, okay, that I need to go through. Now I recognize I can't solve this using box A. I'm going to solve it using box B. 15 kilograms. This is the force of A on B. This is the force of friction, which was 22 newtons. All right, next thing I want to calculate, F net. M times A. 15 times 1.5 should be 22.5. It was 1.5, right? 1.2, sorry. Okay, so that's going to be 15 times 1.2. Okay, so 18 newtons. Okay, everybody all right with that? All right, so my net force is 18 newtons, okay? And in this situation, F net equals 22 newtons, actually negative 22 newtons, plus the force of A on B. All right, so what have I got to do with this 22 newtons? Subtract it over to this side. All right, so the force of A on B is going to be F net minus negative 22 newtons. Okay, so that's going to be 18 newtons positive because it's to the right, okay, minus negative 22 newtons because it's to the left. All right, so we're looking at 40 newtons, right? Okay, so the force of A on B is 40 newtons to the right. What's the force of B on A? 40 newtons to the left. Okay, so it's really just a Newton's second law problem until the very last step when I go right, equal but opposite. Now I'm done. Okay, that's all we have to do with the Newton's third law step is remember equal but opposite. Okay. What else?
Do you have a vector question?
A vector question? Okay. Okay, so the box, 20 kilogram box on a level surface, being pulled by a oh, that's too big. Sorry, that force is too big. It's going to fly off the table. That'll work. Okay, so it's being pulled by a force of 100 newtons angled at 30 degrees. Okay, and it's moving along the table at a constant speed of 2.5 meters per second. I want you to calculate mu in this situation. Okay, so what's the coefficient of friction in this situation? This one will take you a bit. There's a few steps involved in this. Remember, this is a vector question, okay? So there's going to be some vector calculating and a little bit of trig. But make sure that you draw a free body diagram so you identify all the forces. Florence, question?
So is the box moving horizontally?
Yes, the box is moving along the table at 2.5 meters per second. Constant velocity of 2.5 meters per second. Okay, so I want to complete my free body diagram, but before I do that, I want to eliminate that one angled force by finding its what? Its vertical and horizontal components. I need its vertical component, okay? It's not that that's not important, okay? So first thing I want to do then is find its horizontal component here, okay? So that's going to be cos of 30 times 100. Oh, works better when it's on. Okay. Cos of 30 times 100. All right, so we're looking at 86.603 newtons. Okay, so that's the horizontal component. I also need to find the vertical component. Okay, so that'll be the sine of 30 times 100. That'll be 50 newtons. Okay, so those are important because the box isn't moving 30 degrees above the horizontal, is it? Okay, it's being dragged along the surface, which means its motion is the vector sum of all the forces that are acting on it. And what I've done is eliminate an angled force so that all my forces are either horizontal or vertical. Okay, so that simplifies things a little bit. Now I can get rid of that. All right, so what I'm going to do is I'm going to take this and put it here on my free body diagram. I'm going to take this and put it here on my free body diagram. Okay, actually I'm probably going to move it just a little bit more this way. Oh, don't come apart. Okay, I know I have a force of friction. Okay, what other forces have I not drawn on here? Force of gravity. Okay, so that's 20 times 9.81, 196.2 newtons. What other force is still missing? Normal force. Okay. They want me to get mu. Okay, well mu is part of this force, part of force of friction. Force of friction is mu times the normal force. I don't have normal force and I don't have force of friction. But can I get them?
Normal force.
I can get normal force and I can get force of friction. In fact, force of friction I already have. What is it? Right, it's negative 86.603. The key words in this question were constant velocity or constant speed. That means the force forward and the force backward are equal. All right, so I know my force of friction is 86.603 newtons, so I've got that. Okay, if I want to find mu, I still need normal force. Same idea here. The box is not moving vertically at all. So what do F normal, F vertical, and force of gravity add up to? 0. Okay, so I can calculate my normal force because I know the vertical component of that pulling force is 50 newtons, okay? And I know that the force downward is 196.2. Okay, so what that means for me is that normal force is 196.2 minus 50. So it's 146.2. Everybody okay with that? Okay, now that I know that, now I can calculate mu. Mu is going to equal the force of friction divided by the normal force. And mu is usually a decimal. It's usually less than 1. Okay, and it looks like that's what's setting up for me now. So 86.603, okay, divided by 146.2 will get me my mu. So divided by 146.2. Okay, so my coefficient of friction is 0.59. I have two significant figures. And there's no units on mu. How do I know that? Well, what did I just divide? Newtons by newtons. So newtons cancel. Okay, coefficient of friction is just that. It's a coefficient. It just relates two forces. Okay, so it has no units. Okay, is that one fairly involved? Like there's a lot of steps on that question. Okay, again, not any really complex math. Okay, the most complex math was doing the trig, right? The rest of it is just adding and subtracting. Okay, but there's a lot of reasoning that goes into a question like that.
And if there was no constant speed, we'd have to do single forces to get force friction?
If there was no constant speed, then I would have given you the acceleration. And so you just still calculated net force that way, okay? And then done sum of all forces to get force of friction. Okay? I mean, we did sum of all forces to get force of friction too. We said forward force equals backwards force. That's sum of all forces. Okay, all right, what else, guys? That was a good one.
Work energy.
Okay, work
Like
energy.
the difference between the two? There's work energy theorem and work energy, right?
No, same thing. Yeah, work energy theorem is work and energy, right? If I'm doing work, I'm changing the mechanical energy. If I'm not doing work, then EI equals EF, right? So if we're looking at this, okay? The work is the change in mechanical energy. So that's EF minus EI. If there's no work being done, then EF minus EI is 0. That means EF and EI are equal.
So that's mechanical.
Yeah, mechanical energy, right? So it would be,
If there's no work being done, it's mechanical energy.
pardon me?
If there's no work being done, it's mechanical energy.
Well, it depends, right? Remember that what we're saying here is that work equals EPF plus EKF minus EPI plus EKI, right? So it's always mechanical energy because if you have either one of those, you have mechanical energy. Okay? So even if all I'm doing is stopping a car using its brakes, I'm only changing the kinetic energy, but when I'm changing kinetic, I'm changing mechanical, right? We're just saying that in a situation like that, if it's on a level surface, EP and EP are 0. Right? They're not changing at all. Is that all right? Okay, what else, guys? Okay. If, oh, sorry,
Can
Ashley.
you do one with the sign that's hanging in the
A static question? Yeah. Okay. Signs hanging, not moving, has a mass of 100 kilograms. Calculate the tension in cable A. So, what's the net force in this question? 0. Sign's not moving. That means the forces up and the forces down are equal, the forces side to side are equal. Not that we're concerned with the forces from side to side at all here. All right, so the force of gravity pulling on this side is going to be 981 newtons. Everybody okay with that? And just 100 times 9.81. What's pulling up on this side? Right, I'm going to do force of gravity divided by 2 because each cable is supporting half of that 981 newtons. Okay, so each one of those cables has a triangle that looks like this, with the middle line being their half of this 981 newtons. So that's going to be 490.5 newtons. Okay, so each one of those cables has a vertical component of 490.5 newtons. Now, this angle here is no longer 90. If I'm looking at an individual triangle, it's now 45 degrees. Okay, now I can calculate the tension in cable A because I know the adjacent side, and I'm looking for the hypotenuse, and I know the angle, right? So if I know that the cos of 45 equals 490.5, the adjacent side, divided by the hypotenuse, I can solve for the hypotenuse. A will equal 490.5 divided by the cos of 45. Okay, so 693, well, we only have, two significant figures. So 6.9 times 10 to the 2 newtons. Okay. What else? Well, if there aren't any more questions, then I would suggest doing those like 7 review problems, okay, that I posted with your review package. Those are all old exam questions. They'll give you some idea of what to expect. Maybe have a look at those or look at a few from your worksheet. Julia, question?
I think it was a super convoluted, Newton's third law question.
I already did. That was the 2 boxes. That's as super convoluted as they get. They don't get more convoluted than that 2-box question. And since I told you that's exactly how I'm going to test it on the test, that's your Newton's third law one. Yeah. I mean, we can do another 2-box question if you want, but I mean, they're all the same.
You don't have to look at more convoluted one, or?
Not really.
Okay.
Not since I wouldn't want to show you one now that's more difficult than what I'm going to ask you on the test. Right? It wouldn't make much sense to do that.
Will the answers be given for the 7 questions?
Yes, they're on there in bold after the question. Okay, well, then work on that there, guys. And if more questions come up while you're working on it, let me know and we can go over those.